Welcome to the Physics and Astronomy Department Colloquium. Today, we're really honored to have Professor David Gutzler from UNM, Earth and Planetary Sciences Department. He's retired, but he's also a member of the IPCC and is the lead author on the North America chapter of the most recent assessment that was released on Monday. Dave is an excellent speaker. He has done a lot of work communicating climate change science to the public and to lots of non-specialists in many, many settings. He's really well known throughout New Mexico for his work on communicating the impacts of climate change in the arid Southwest. He is a physicist by training. He got a bachelor's in physics and then moved into atmospheric science for his master's and his PhD. He's best known in New Mexico circles for his work on the southwestern monsoon and variability in summer precip because of the southwestern monsoon and the factors that drive it. But more recently, he's been working on climate change over the long term, and he's going to tell us about the IPCC and its work and its outlook. So take it away, Dave. Thank you so much for coming.
Thanks, Masumi.
Can I just do a sound check? Can you hear everybody? Excellent.
Sounds okay.
Those on Zoom, are you okay? I will check, Dave.
Okay.
Yeah. You've got a pointer.
I have a pointer. I want to thank my colleagues in physics here for asking me to give this talk. It's fun to be back on campus. I still get here from time to time. I retired from the teaching faculty about a year ago, thinking that this IPCC effort was within a month or two of being completed. It has dragged on thanks to the pandemic. So the timing of this talk is dictated by the fact that the volume on which I was a lead author was formally embargoed until it was formally approved by governments on Monday. And so what we'll do today is spend a little bit of time talking about physics, and I'll apologize in advance for the amount of time we'll spend talking about policy and communication and things like that. I'll tell you a little bit about how the IPCC works, and then we'll snow you under with 10,000 complicated graphics. I promise there won't be that many. Talking about what has come out of this report. And then I want to spend a few minutes at the end talking about the effectiveness or lack thereof in terms of the communication between the scientific community and the policymaking community. Because after all, this whole effort is supposed to be designed to inform policymakers. There's a graph here that shows a graph that's not really terribly new. It's based on new modeling results, but it shows a result that is not much different from what previous assessments have looked like. It shows the observed 20th century and early 21st century temperature curve in black, a bunch of model simulations shown by the brown envelope, in which modelers put in their best estimates of the forcing functions that should affect the globally average temperature, mostly greenhouse gas concentrations, solar variability, and aerosol pollutants changing with time. And you're supposed to get the idea that the models are doing a pretty decent job simulating observations. When you take out the human-caused forcing associated with greenhouse gases and aerosol pollution, you get this sort of aqua envelope variability that fails to capture the warming that has been very clearly and convincingly observed over the past half century. And so this is kind of ground zero for why we're doing this, which is that there's what is now regarded generally as incontrovertible evidence that much of the recent climate change that we've experienced is associated with human-caused forcing. That's an issue for policymakers if they choose to decide to do something about it. Okay. We say clicks. Okay. A little bit of background, both to get you acclimated to acronyms, which are going to infest this talk, and I'll apologize for that too. But my own involvement in this whole IPCC process began with the previous assessment, which came out about 8 years ago, in which I was a lead author. I think Masumi called me the lead author. And let me assure you, I'm not the head of the whole thing. I'm one of a couple hundred people who are called lead authors, even though we're just the troops. And so in the previous assessment, I was a lead author in what we call Working Group 1, which is actually the science volume of these assessments. And I worked on a chapter in which we analyzed that curve I just showed you, where we rigorously, as best we could, tried to determine what the causes of observed climate change were. This time around, I also participated in the successor volume to this previous one. Now we're into the 6th assessment report, so-called AR6. And there was a physical science volume for that came out last August. And so I contributed to a couple of chapters in that volume, but my principal role was in so-called Working Group 2, which has produced this volume. This is the one that just got approved this week on the impacts of climate change and adaptation strategies for coping with climate change. And so in this volume, I was a lead author, which is one step above a contributing author, to the chapter in this volume on the regional impacts of climate change on North America. So I've been doing this for a while, and I promise I won't do it again. I will be retired. This, by way of introducing the results, I wanted to show, this slide was the first slide I showed in the last class I taught before I retired from the teaching faculty on global climate change. And it shows a version of that same global warming curve. This is just the observations going up through 2019. And this is the standard global warming curve. It shows globally averaged surface air temperature averaged over the whole planet, annually averaged, going back to the middle of the 19th century. And we can ask a bunch of questions based on that curve. And the distinction, I want to do two things with this list. One is to motivate the way the IPCC organizes its assessments. And secondly, to make a distinction between scientific or positive kinds of questions that we can ask and value-laden policy questions that cannot be solved by the scientific method. So there are some pure physical science questions we could ask about this curve. One could ask whether it's real. Are the data actually good enough for us to formally detect a change, in this case, in temperature? That's a data-based question. How good are our data? There are actually error bars on each of those annual averages. And there's a big data-centric set of questions about detecting climate change in temperature or all kinds of other variables. Secondly, if we think the climate really is changing, we can ask what's causing it. And that's called attribution in our business. So attribution is a much more process-based question. It's what's causing the change that we see. And then if we think we're reasonably confident in our attribution understanding, then we might get bold and say what's going to happen in the future based on our understanding of processes that have already caused climate change. These three questions are organized by the IPCC into that first volume that came out last August. That's a couple thousand pages long, answering these questions. The volume that just came out is about whether any, and this is a wonderfully interesting question, mostly in physics, a little bit of chemistry, a little bit of biology, but it's essentially a bunch of physics questions as to what's making the climate change here. Then to make this of interest to, that would be a terrific academic exercise if it didn't affect people's lives. But in fact, there's a whole host of impacts of curves like this, not so much of globally average curves, but the expression of that kind of curve locally that affect ecosystems, that affect economics, that affect people's livelihoods. And so we can try to enumerate the impacts associated with climate change and ask to what extent we can attribute impacts going on in the world to climate change. So if wildfires are increasing, and it seems like they are, is there a way to attribute the increase in impactful wildfires to climate change? There's a timescale question associated with those impacts. Are they urgent for anybody to address? And the timescale impact of that is actually kind of a science question too. There's two colors shown here, and I should have put that box up earlier. The blue questions are questions that we might reasonably address using evidence. In other words, they're science questions, and using the scientific question, we can try to address them. But then when we start talking about impacts, we could ask, are they important? Does anybody care about a certain impact? We can measure impacts as applied physicists. They may or may not matter to our elected officials or business leaders or anybody else. And so whether or not climate change is an important thing is really kind of a value-laden question. And scientists can't address that with a scientific method. We can't say whether society should invest a boatload of dollars in changing our energy systems around if those dollars might be used to do something else, right? So attributing values and importance to these questions gets tricky and involves values and gets us outside the scientific arena. As we'll see, a lot of the impacts involve big generational inequities and big geographic inequities that make this whole value-laden importance question very difficult. Why should I pay if the impacts are going to affect somebody in Asia? And then, so these sorts of questions are what were addressed in the IPCC volume that just came out. And then there's a third set of questions, which is what can or should we do? If we think people are causing that increase in temperature, should people act? And we understand enough to do something about it. What can be done? What should be done? And again, what can be done is kind of a science and engineering question. But what should be done is much more value laden, and that's a question for policymakers. Okay, so there's a third volume that's coming out in a couple of months that is directly associated. The whole volume is about the mitigation of climate change, which is about this set of questions 6. All right, so that's where we're headed. I'm not going to spend an awful lot of time talking about these response questions because that's coming out in the next volume. I've got 5,000 or 6,000 pages of IPCC report to summarize here in 50 minutes. So I'll stick to the science and the impacts for the most part. You can ask questions about mitigation and responses later if you want. Okay, here's a physics slide, and I'm just going to blitz through it. And part of the reason is that this is old stuff, And there's really not much of a scientific debate about what's shown here. And it's what we would call a solved problem. All right. And that is that we have data, and we're quite confident in the data that show a monthly carbon dioxide concentration in the air at the surface on the top of Mauna Loa going back to the late 50s. And that's what that curve looks like. There's a nice seasonal cycle associated with photosynthesis in the Northern Hemisphere, but that's going up unambiguously. So there's no debate about whether that curve is real or significant. We know where the extra CO2 is coming from. It's coming from mostly burning fossil fuels, but there's absolutely no way to explain the upward trend in that curve without blaming people. And there really is no debate about that. And so I'll just assert it that, you know, this is what's coming out of the tailpipe of your car, unless you're driving an electric car. And we know that this curve looks like that if we put it into context over the entire Holocene, over the last 10,000 years. So CO2 concentrations bounced around. We know this from ice core data until the Industrial Revolution, and then it did this. And it's still heading up dramatically fast. And that's because of us. Finally, there's no debate at all over the reality of why a curve like that ought to be related to surface temperature. So we know how the greenhouse effect works. There's a cartoon here. The effect of CO2 is represented by that bent green curve right there. So shortwave radiation comes in from the sun. We have certain trace gases in the atmosphere called greenhouse gases that preferentially absorb the longer wave radiation emitted by the surface of the planet because it's colder. And so we have a bunch of energy recycling going on in which the emitted radiation that's trying to cool the surface gets absorbed in the atmosphere and re-emitted back down. And that's been known since at least the 19th century. And the general reality of how this works is not at issue. And in fact, it's very well modeled too. So we know that there are certain greenhouse gases that do most of the work here. There are plenty of other uncertainties modeling the climate, but this cartoon is not one of them. So that's the basis for why we're doing all of this, is we know that these things are happening. And we know enough physics to understand that all else being equal, more CO2 is going to mean a warmer planet at the surface. Okay, the IPCC, which we're about to talk about, was established in 1988. And you can see the profound impact on that CO2 curve that the IPCC has had. Everything changed in 1988. Thank you for laughing, Greg. Okay, so the IPCC was established by the United Nations. So it's part of the United Nations. It is charged with the UN with assessing peer-reviewed information that's relevant to climate change. So it's set up as an advisory group to the United Nations to provide reports assessing the state of the science about climate change. So these giant reports are assessments of other people's published papers. The IPCC doesn't carry out original research. That's a little bit of a fudgy comment because, as we'll see, there's lots of new modeling that goes on with every one of these reports. But everything that I'm going to tell you that's in these reports is supposed to be based on peer-reviewed literature and our assessment of that literature, especially when there are conflicting results that come out. So if it was started in 1988, there have been 6 so-called assessment cycles. We're getting to the end of the 6th one. And as I told you a few minutes ago, I've been associated with AR5 and AR6. Okay, VAR, SAR, AR4, we're just getting started with the acronyms, and then I'll apologize for that. Okay, after the first assessment report, the policy contingent that is attached to the IPCC was established. So there was a big meeting in Rio de Janeiro called the Rio Summit that generated an international treaty called the UN Framework Convention on Climate Change that formally entered into force in 1994. Almost every country in the world is a party to it, including the United States. And the way you do these international treaties is that this, what this framework convention says is we have a problem and the international community solemnly swears we're going to do something about it. End of statement. So there's no attempt to say what you're going to do about it. There's an aspirational goal in there that's long gone about targeting CO2 emissions at the 1990 level worldwide. But this provides the policy superstructure that allows subsequent negotiation to actually maybe do something about climate change if enough countries decide to do it. So the IPCC is now exists to support and inform developments under the auspices of this international treaty called the UN Framework Convention. And so to some extent, some of the questions that get asked and the way the reports get structured are in response to queries from the Conference of the Parties to that framework convention. So there's kind of a back and forth here between these different assessment reports, first, second, third, fourth, fifth, and sixth, and different policy developments that occurred at annual meetings of the Conference of the Parties to this framework convention. So the most recent one of these conference party meetings got a lot of press. It was in Glasgow a few months back. And these Conference of the Parties meetings have turned into big spectacles. I'd love to go to one. I've never been to one, but you know, there's lots of protests and people running around protesting and wearing fancy costumes and bureaucrats bloviating and you know all that kind of spectacle stuff. The IPCC is supposed to provide the science to inform those discussions. All right, so after the fifth assessment report, there was actually an agreement that tried to put some teeth into the framework convention about doing something about climate change. And so to some extent, this most recent report is has been restructured in response to the policy needs of the people who were parties, the countries that were parties to the Paris Agreement. And there's a bigger emphasis on impacts as opposed to just basic science, because it is thought by the policymakers that the policymakers have finally swallowed and accept the basic science as part of agreeing to this Paris Agreement. Okay, so the Paris Agreement, which you hear a lot about in the news, has this goal of stabilizing global average temperature change to well below 2 degrees Celsius. And so you will be shortly seeing lots of plots that show a various impact or the change in some climate variable associated with global warming of 2 degrees. There's an aspirational goal of limiting climate change even farther and limiting it to 1.5 degrees C. And so an awful lot, as we said, is associated with trying to make this work. Well, I won't spend too much time talking about this, but there really isn't an awful lot of teeth to this Paris Agreement. It's based on non-binding nationally determined contributions to limiting greenhouse gas emissions. So there's very little enforcement here. It's all voluntary. It's hoped that this will be a first step by the policymakers in starting to limit greenhouse gas emissions to make it easier to make more stringent restrictions later on. And there's a good reason for that. This is the way things were done in a previous environmental challenge, namely stratospheric ozone depletion, where the first international policy to limit the CFCs that were taking out the stratospheric ozone was done much like this. And once the technology had evolved to make it easier to withdraw CFCs from the market, then the restrictions were made much more stringent by amending this agreement or the agreement like it. And so there was a sort of a virtuous feedback cycle that happened where once you got the technology underway to address the problem, it made it easier to ramp up and accelerate moving away from environmentally harmful products. Okay, so we have the Paris Agreement and we have this emphasis on global warming levels of 2 and 1.5 degrees. All right, so the main assessment report has these 3 volumes that we've already talked about. Within each volume, they each have on the order of 15 to 20 chapters. And if the chapter is to one of these volumes, like a university department is to the university itself. So that each chapter is, it's kind of the intrinsic assessment unit. And the chapters do their work largely autonomously, and we only come together and meet as a whole a few times during the course of developing one of these reports. So each one of these chapters has a couple of coordinating lead authors. The coordination goes with the other chapters. Something on the order of a dozen lead authors. That's what I've done the past 2 assessments. And then a roster of lower level contributing authors that are asked to provide specific expertise on topics where the lead authors don't think they can cover. So we had these 3 volumes in the last report. And now we've got these 2 volumes that have been released so far in AR6 and one more, which is the mitigation volume coming in a couple of months. In addition, there's a few smaller special reports that have been issued as part of this assessment cycle. But what I want to emphasize here is some reorganization that was done in response to the Paris Agreement, which is that they decided they didn't really need a 2,000-page physical science report that spends 150 pages trying to convince policymakers that global warming is real, because again, the idea is they've accepted that in the Paris Agreement. So some of the basic science material has been condensed into a few chapters, and there's more emphasis in this physical science volume, results of which I'll show you in a minute. We'll finally get there, in providing direct support to what it's thought the policymakers want to see, which is all about these impacts, right? Does anybody care? What are the impacts on people and ecosystems from climate change? And that's what's in volume 2. So among the things they did, in addition to those 3 categories of authors, was they created a new category of author in Working Group 2, the impacts volume, in which they embedded a mole. So there's an awful lot of economists and social scientists and people like that in volume 2, but the IPCC decided to recruit one lead author who was a physical scientist in each continental chapter. So North America, South America, Europe, Australasia, in the Working Group 2 impacts volume. And that's what I did. So my role this time around was I was the designated physical science mole in the North American impacts chapter who had Working Group 1 experience in the physical science volume. And that's why I ended up spending way too much time on Zoom meetings and getting dragged into several different chapters in Working Group 1, in addition to being a lead author for Working Group 2. It's not clear I knew what I was getting into. All right, that's special report that came out a couple of years ago on 1.5 degree warming. This is one of those 3 special reports on the slide before. We're finally getting to some results, I promise. And this shows something about urgency. Okay, so a bunch of small island nations objected to the Paris Agreement because they said, even though they signed on to it, they said that at 2 degrees of warming, we'll be underwater. And so it's not good enough to set a goal of 2 degrees of warming. We need 1.5 degrees of warming. So at their request, the IPCC undertook a special report on the difference between warming of 1.5 and 2 degrees and whether it made much difference and what it would take to keep warming to 1.5 degrees. And so a plot like this was developed. And so one of the things you can do with climate models is you can reverse engineer them. You can say, I want my model to end up with warming of 1.5 degrees warmer than the 19th century temperature, which is our baseline. What kind of emissions pathway will get us there? And of course, that's not a unique solution. And so we have these emissions pathways shown here. And so the big punchline out of that was that if you want to limit warming to 1.5 degrees over 19th century temperatures, we have to take emissions that look like this, something like 40 billion tons of CO2 per year. And almost immediately, you need to start reducing them. That's how you limit warming to 1.5 degrees. And then within all these different pathways, there's kind of 2 groups. There's groups that require very rapid, very quick reductions in CO2 emissions. And they asymptote out at something, you go negative finally, but the last 30 years or so of the century, you're at some standard level. Or you could say, oh, we can't do this too fast. We need more time before we reduce emissions. And in a model, what you can do easily enough is you can say, that's fine, let's just follow this gray line here. We're not reducing emissions until more like 2030 or 2035. Down they go, and then I need negative emissions. We need to draw CO2 out of the air in order to get back to only 1.5 degrees of warming at the end of the century. This is called an overshoot pathway. And as I said, it's an easy enough thing to do in a model. But one of the conclusions, and the overshoot pathways, needless to say, generated a lot of interest among the industrialized countries. They said, okay, we can make it to 1.5 degrees, even if we put off emissions reductions for a decade. But one of the things that has come out of the report that was released this week is a list of the rather irreversible consequences, the reasons that that might be a bad idea for policymakers to rely on things like glaciers melting and not coming back, ecosystems, habitat destruction, lots of bad ecological things happen if you allow the climate to warm up and then try to bring it back down. So this is the kind of thing that gets assessed in these reports. And one of the basic conclusions that's reiterated in the main report is the punchline here, which is if you want to limit warming to 1.5 degrees or even 2 degrees, I won't show you those curves, we've got to start reducing emissions very soon, right? This is not something that can be put off any longer. The IPCC is not policy prescriptive, so this is stated very carefully. It's always, if you want to do this, then here's what you got to do. So the IPCC is not in the business of prescribing that this is the path that the world should take. It's that if you want to limit warming, with that big if, to 1.5 or 2 degrees, here's what you have to do to make it work. Okay. One last, I think, bureaucratic thing. There I am. It's easy to see that this whole thing would have fallen apart without me. This has taken almost 5 years. Okay, and that's a criticism we'll come back to at the end. over the course of years, this team of authors was assembled. Within the United States, there's a group called the US Global Change Research Project. They solicited nominations of authors way back in 2017. We're all volunteers, so there's no compensation attached to being one of these authors. Author teams for each chapter were assembled, and then we started writing around 2019 after this first lead author meeting, and went through 4 drafts of the report before final approval earlier this week. Last weekend is really when it happened. I've racked up a ridiculous number of frequent flyer miles. You can see I did not go to the meeting in Addis Ababa. I was brought on in this step, but I've been hauled off to meetings in Trieste and South Africa and Nepal, and the sort of thing that diplomatic type people doing UN related work tend to do. There's angst about that. We'll come back to that in a minute, but our carbon footprint is kind of outrageous. It's not too obvious how you get this done on a worldwide basis without that, but we'll see. The other thing I wanted to emphasize is that after each one of these these drafts, there's a review process that generated, I haven't seen the count yet, but I'm sure somebody will come up. It will be in the tens of thousands of review comments. And this is the step that involves external accountability. So a big worry among the group of authors is groupthink. It's easy enough to sit around in a meeting room at the Yak and Yeti Hotel in Kathmandu and agree with each other. And the way we hope we minimize that kind of groupthink is by opening up these drafts to expert and government review. And we have to address each and every one of the comments that comes up. A lot of climate modeling gets done. There is a worldwide coordinated climate modeling effort that is distinct from the IPCC, but coordinates with it, called CMIP, the Coupled Model Intercomparison Project. A new generation of models is used for each of these assessments. So we are now looking at CMIP 6 climate models. These are climate models developed independently by research centers all around the world that agree on a common set of modeling experiments to run to make all the models comparable. What's new this time is there's a publicly accessible interactive atlas where any of you who want to take a look at CMIP 6 data can just go to interactiveatlas.ipcc.ch and generate plots like this. That's just a screen capture, and download the data. So that is very cool, actually. And we also generated these 2-page fact sheets. So here is from Working Group 1, a set of projected temperature and precipitation maps for North America for different global warming levels, right? So these are all these CMIP 6 models, and we average all the models together at the time at which they reach prescribed globally average surface temperature change relative to the late 19th century. That's called the global warming level. And so here's what temperature change and precipitation change across North America looks like for warming. That's 1.5 degrees above late 19th century levels globally, right? So this temperature change, if you average that map globally, it would have to average out to 1.5 C area averaged. It's a lot warmer than that in the Arctic. It's not so warm in the tropics, right? We see tremendous Arctic temperature enhancement of global warming. For northern winter and northern summer, and here's the precip maps. I won't go into them in an awful lot of detail. These are not too much different from the previous generation, except in details, but a little bit accessible, and these fact sheets are designed for things like school teachers and so forth. So they are out there as well. Okay, so what are we actually seeing in this assessment. Sorry about all the words. From working group 1, the physical science volume, we simply reiterate conclusions that have already been reached in previous versions of this assessment. Earth's surface is warming, widespread, rapid, intensifying, and unprecedented climate changes in multiple variables. And that's just sort of a general umbrella statement. They've now cranked up the confidence in the attribution statement to now say it is indisputable that human activities are changing the climate based on all the evidence that's out there. And here's the result we've already talked about. Unless there are immediate, rapid, and large-scale reductions in emissions, limiting warming to 1.5 C, the aspirational Paris Agreement goal, will not be possible. And then another conclusion here that is confirms a previous result is actually really important for policymaking, which is that except for some of these overshoot scenarios, global warming is very highly correlated with the total cumulative greenhouse gas emissions that have been emitted since the late 19th century. Okay, and so that's true looking backward in time, which is this gray part of this curve, and it's true going out forward in time, right? So the x-axis here is not time, it's cumulative emissions. The reason that's important is that it supports the hopeful conclusion that comes out of all this, which is that policymakers can do something. They can limit total cumulative emissions going forward. And to the extent you do that, you keep this curve from reaching, farther out here up towards 2.5, 3 degrees of warming. Anything the policy making community chooses to do to limit total cumulative emissions, according to this projection, will mitigate climate change and its impacts. Okay, I'm going to zip through some of these maps and get to some of the more new stuff. So we have lots of maps that look like this from working group 1. This is temperature change. If we look at simulated 1 degree of warming, we've already passed that. We're at 1.1 now. And so if you model 1 degree of warming, you effectively can validate your model because that's already happened. And you're supposed to look at this map and say, that looks pretty good. And if I click on to the next slide soon enough, you'll agree with that before I give you a chance to look at the details too carefully. There are some things that a lot has been made, for example, of this little patch of cooling south of Greenland in the North Atlantic Ocean. There's a hint of it in the simulations, but not enough of it. Maybe that's a hint of some important changes in the ocean circulation in the North Atlantic. And as we allow these model projections to go forward, not surprisingly, we see, it just gets redder and redder. This is probably not a planet you want to live on, but that's 4 degrees of warming, right? And so we have lots of maps like that. Here are hydrologic changes done the same way. Basically, the precipitation pattern, the pattern of change, is an intensification of the existing pattern of global precipitation, where wet areas get wetter and dry areas in the subtropics tend to get drier. What else do I want to say? If we combine the precipitation changes with temperature, then what tends to happen is that even in places where precipitation doesn't change much, like New Mexico in these, right? So New Mexico's there, maybe in the browns a little bit, but not terribly intensively. Nevertheless, if you increase temperature by 1.5 or 2 or 4 degrees, then you increase the evaporation rates off the surface. And for the same amount of precip, the surface dries out. And so we get a big signal in drier surfaces in the Southwest, which is bad news for us locally. And then here's my favorite plot from working group 1. I'm going to skip down to this one at the bottom. This is the sea level change under global warming. And we have various curves going up. Sea level is rising, mostly because as you warm up the oceans, water becomes less dense. It's got a floor at the bottom. So if it's going to expand, it has to go up and sea level rises. Previous assessments have only gone out to 2100, but this is one of these variables that changes a lot and changes slowly. So they got brave and had enough confidence in the modeling of sea level to extend this curve out beyond 2100 for another couple hundred years. And instead of on the order of ½ a meter of sea level rise, now we're 10 times that much, perhaps. And that's because once you get out beyond the 21st century, the major ice sheets start to melt on the continents and literally add more water to the oceans. So it's not just a thermal expansion effect, it's the volume of water sitting in the ocean. And so if policymakers at all care about what happens in a couple hundred years, then there are just profound changes that might happen with, you know, enormous uncertainty estimates. And, you know, ominous things in the fine print like sea level rise greater than 50 meters cannot be ruled out. So a lot of uncertainty here, but this is the first time that one of these IPCC assessments has stated that. The last assessment simply had this plot, which is really essentially the same as this plot here without this extension to 2300. Just, you know, this is temperature again, and not surprisingly, September Arctic sea ice in these projections, that's the minimum time of year for Arctic sea ice. It's basically practically ice-free by the time we get to the late part of the century. And the ocean takes up carbon dioxide, usually in the form of carbonic acid. And so as we keep loading the atmosphere with CO2 and it's taken up by the oceans, then ocean acidity rises and the pH goes down. Okay, I'm not gonna go through this risk propeller. If we go into working group 2, now we're talking about how those changes that we just talked about are expressed as impacts that matter to people and ecosystems. So water supply, food supply, extreme events, wildfires, human health, et cetera. And the extra components of the assessment that come in here are that it's not just climate change itself that matters. In the argot of this impacts community, the risks associated with the climate change are a function not just of climate change, which here we call hazards, but also the exposure and vulnerability of people or ecosystems to that climate change. So if you have a house on the coast and storms are getting more severe, there might be a climate change hazard associated with more intense hurricanes or severe storms. You could address that risk by limiting climate change, but you could also address the risk by strengthening your house and changing the building codes so that the houses will withstand stronger storms. And that diminishes the vulnerability of in this situation of that climate risk. You could also diminish your exposure to that climate risk just by moving away from the coast. But people don't like to be told to move away from the coast, and the construction industry objects to changing the building codes. So it's not clear in all circumstances that changing exposure or vulnerability is any easier politically than limiting climate change. Okay, so part of what I did in this assessment was to take some of those maps we just looked at and help to translate those climate changes in ways that make them relevant to this sort of risk assessment. So for an example, we've already looked at maps like this. This is temperature change across North America for 2 degrees and 4 degrees of warming. And we see this emphasis on Arctic enhancement of temperature change. But another way to express temperature change, which addresses the risk to people living in a climate where it's just too hot to work and live, especially outside, or if your access to air conditioning is limited, is the number of days per year when the temperature exceeds 40 C. And so we can express our temperature change that way instead of just average temperature. And when you do that, you get maps like this. So here are the changes down there for the number of days per year when the temperature is over 40 C. And now, instead of emphasizing the Arctic, we emphasize the places that are just going to get bloody hot if the climate warms up. And we emphasize risks associated with heat around the Gulf Coast and in the southwestern desert. The part that maybe is not quite so immediately self-evident is that these risks extend all the way up to the Canadian border under 4 degrees of warming. So there's a translation into impacts-related climate hazards that takes place in the second volume. And so we end up with gigantic tables like this. For each of these regions, we have all of these different climate changes, different variables, temperature, humidity, wind, snow, and ice. For all these different regions, that's in working group 1. How is the climate going to be changing? And then in working group 2, we assess the literature looking at the effects of these climate changes on climate risks by adding the exposure and vulnerability elements. And we end up with this table looking at all kinds of impacts to energy resources, poverty and livelihoods, health, community, on and on and on, for all those different climate variables. And in the next 3 hours of my talk, we'll go through every one of these. But if you want to be a glutton for fun, that's what we do in this assessment. In this report, there's information about all of these. Every one of those colored squares is an assessment based on published literature. So that's why it took years to do this. It's a big job. So instead of going for 3 hours, let's just summarize and say that what we get out of that outrageous, humongous exercise is, not surprisingly, the notion that climate change risks are going up. And they'll go up over the next few decades almost for sure, because there's no prospect of immediate emissions reductions. We have the risks tend to scale with global warming levels. And remember, the global warming levels themselves scale with cumulative emissions. So we put all those pieces together for policymakers. There's an assessment of adaptation efforts for a lot of those variables. And the basic conclusion is that they can work. And there's an evolving number of adaptation efforts on the local scale that really have worked to address some of these enhanced impact risks. But those adaptations are too localized, too slow, and too incremental to keep up with the rate at which climate is changing. Not surprisingly, perhaps, we do a lot of reactive stuff, right? Big storm comes and causes a lot of damage on the coastline. Oh, okay, maybe we should build a wall. And so if you want more effective adaptation to all those risks, then the conclusion is that what we really need to do is generate coordinated, and the word that's used that's loaded is transformational adaptation efforts. Ladies and gentlemen, that means big government. And so you can tell me how effective it's likely to be for the IPCC to say, we need more coordinated transformational adaptation efforts that get at the changes to the way people live their lives in order to cope with climate change. But that's the evidence suggests that if you really want to try to adapt to what's coming, this is the way you have to do it. And the kicker is that poor countries are vastly more vulnerable to all these climate change risks than industrialized countries like the US. So adapting to climate change involves enormous inequities across countries, geographically, and across generations, right? So if we do nothing, old retired guys like me will probably be just fine. not so clear my kids and grandkids. They're the ones that will pay for the emissions that I emit now, right? Because it's total cumulative emissions that matter. So there are huge climate justice questions that come up that will need to be addressed one way or another. Okay, that's the basic conclusion. We can go, I'm going to skip wildfires. Let's just, so here's the kind of ridiculous, too complicated graphics that infests our reports because we're trying to jam too much information into a mere 1,500 or 2,000 pages. This is a map of North America showing projected rates of sea level rise in various places, along with a quick assessment of whether or not those places are starting to impose adaptation measures to do something about the fact that sea level is rising. And so sea level is rising pretty much everywhere. The only place that sea level is not rising is actually right around Hudson Bay because of post-glacial rebound there. The land is actually rising nearly as fast as the ocean. But there's a huge range of adaptation plans for rising sea level that vary from place to place, not just from one country to another. And so the general conclusion here is that adaptation plans are happening, but not enough, not quickly enough, not coordinated enough to really keep up with the rise in sea level. Quick thought that there's still science to do. This is not a solved science problem by any means. One of the things that is still out there is the fact that our models are not real consistent about how much we should expect the climate to warm up for a prescribed level of CO2 rise. This is the so-called climate sensitivity problem. If we take a look at, if we look at that blue bar, that's the previous generation of climate models used for the last assessment. And we ask the question, how much does the surface temperature change globally if we double CO2 content and run the model to equilibrium? Okay, that running it to equilibrium is not realistic, but it's a nice controlled way to compare models. And so if you do that, if you run your model for 1,000 years and do it 1,000 times using pre-industrial CO2, and then you double the CO2 and run the models again for 1,000 times, how much does it warm up? Well, some models warm up 2 degrees and other models warm up 4.5. Yikes. In CMIP6, newer, better models by many estimates, and justifiably so, but that range is even bigger. They do tend on average to warm up a little bit more than the previous generation of models. They're more sensitive to CO2 emissions, but we would very much like this range to be a whole lot narrower. And the bad news is it hasn't really narrowed much since during my career. So that's an outstanding problem that has to do with the strength of feedback effects in climate models. We need more clever physicists to figure this out. All right, I want to end up here with a few words about science and policy. So one of the things that's new in the report that just came out for North America is that there's now enough of a refereed literature on science communication and science policy interactions that we can assess the literature on public acceptance of science. So we did that. And so here's a map that shows an estimate on a congressional district scale of the fraction of adults who think the Earth is getting warmer. Okay? That's not a policy question per se, but for many people, it is implicitly a policy question. And just to be clear, what the IPCC said in the last assessment was that it's unequivocal that Earth is getting warmer. This is just a detection problem. And yet, across broad swaths of both the US and Canada, but mostly in the US, on the order of half the public doesn't believe or won't say that Earth is getting warmer. We got a real problem here. It's going to be very difficult to motivate transformational adaptation efforts or any kind of meaningful reductions in emissions if people won't accept the science that I've tried to present to you over the past 45 minutes. So here is the statement that appears in the report that just came out. Rhetoric and misinformation on climate change and the deliberate undermining of climate science have contributed to public misperceptions of the high level of scientific consensus on climate change, overstating the level of scientific uncertainty, and thereby understating risk and the urgency of a policy response. And we ascribe high confidence to that statement. And we'll see what kind of reaction we get. When the last assessment, this report, the science volume came out in August, here's an example of two ways that that report was disseminated in two not arbitrarily chosen media outlets. So here's what the New York Times had to say. A hotter future is certain, climate panel warns. How hot is up to us? That's the cumulative emissions message. What Fox News reported was scientists, and here they don't mean the scientists that wrote the report, that means scientists they chose to interview, challenge alarm bells in IPCC climate change report, not the end of the world. Needless to say, alarm bells, end of the world, those words never appeared in the Working Group 1 report. They probably were uttered by people talking about the report, but needless to say, it's maybe not too surprising that public acceptance of science is tough when we have this kind of disparate communication and dissemination of the results by the media. Which leads many of us to wonder how much AR6 matters. Do we really need 2,000-page working group assessments if the whole point is to inform policy? There is a group of scientists who are actually more discouraged than I am, there was a story in the New York Times about IPCC authors boycotting future efforts unless the international policy community does something. But recall, it's not our job to tell the policymaking community what to do. Nominally, we're there to provide information to the wise people that make policy judgments. So here's a quote. I'm concerned that we will always face short-term problems more immediately pressing than long-term climate change, which seems like a prescient comment given that there's a war going on in Eastern Europe right now. I worry that the consequences of unabated global warming will ultimately be very grave, etc. Our grandchildren may look back in anger at us for saddling them with the consequences of our irresponsible environmental stewardship. I agree with those sentiments because I wrote them over 20 years ago. And in that time, we have seen what emissions have done. We've generated report after report after report. I don't know what to say. Okay, I'm done. It's a lot of work writing these assessments. I'm tired. It's going to be fun once it's over, but it's writing big reports by committee is a tough slog. We talked about how many frequent flyer miles I came up with. The alternative is 3 a.m. Zoom meetings, which are pretty painful as well. And we did that toward the end of this assessment when the pandemic closed things down. This whole effort is just an extraordinarily cumbersome thing. Rules about style, color choices for the graphs, icons, trying to coordinate and keep messages consistent across chapters and across volumes. It just drives you crazy. The other thing I've learned being part of a big international process where we do meet together when there's no pandemic from time to time is just how astonishingly far out of step with the global community is the United States. I can't tell you how many conversations I've had with people who, just over coffee, where they say, what is going on? Why isn't the United States leading on this challenge? And especially when it comes to just a pure acceptance of the science, that the world looks at us with astonishment about that. And yet it's just been really remarkable for me personally to be able to participate in efforts like this. There's just a profound sense of international collegiality that goes along with trying to put these things together. And I'm very grateful to UNM for allowing me to do it. My department gave me a course release for the effort I was putting into this, and I appreciate that. And it's just been a remarkable process and experience for me personally. So thanks, and I hope we have some time for questions.